In addition to arrays, C gives us the ability to deal with one other kind of data structure. And that kind of data structure is the struct. So with arrays, you can have a collection of items of the same type that are next to each other in memory, a collection that conceptually could be any different size. With structs, you're going to build a collection of items that are potentially of different types next to each other in memory, but any given struct type that you're going to build is going to be fixed size. So an array of char, any size is still an array of char. A struct with 3 fields is always going to have those 3 fields, and depending on the types of the fields, is always going to have a fixed size in bytes. So let me give an example. I'm going to create a thing called goats, and then I'm going to define a struct type. So struct goat is going to have a field called name. My Emacs indenting is awkward, but that's fine. And is going to have a field called mass. Name is going to be a string, so it's going to be a pointer to a character. It's going to be terminated by a null byte. And then mass is going to be a floating point number, I guess in kilos. Sure. Now there's one complication here, and we'll run into that complication when we try to do something with this. But we're going to start off by trying to make this work in a sort of Java style. So we can think of goat as being kind of like a class in Java. And so if we're going to have a class in Java, we want to have a way to build one. So we don't have new in C. Instead, we're going to create a function called makeGoat, which is going to make a goat. It's going to take a name and a mass. And this const here is just promising that we're not going to change the contents of the string during this function. That potentially lets the optimizer do stuff that's useful. We're not going to worry about it too much. So when we go to make a goat, to do that, we're going to call malloc, which is going to allow us to allocate some bytes on the heap. And we're going to allocate bytes equal to the size of a goat. Now, if we stare at this up here, we can figure out what the size of the goat is probably. A char pointer is a pointer, so it is a memory address, so it's the sort of native machine word size, the size of a register. So on AMD64, that's 8 bytes. A float is a single precision floating point number. Single precision floating point number happens to be 4 bytes. So most likely a struct goat is going to be 8 plus 4 is 12 bytes. Now it's possible that there are alignment constraints on where we can put data in memory. On AMD64 for a struct like this, I don't think there are. But on sort of an arbitrary platform, it's also possible that this could take 16 bytes, and we would have sort of 4 bytes of padding at the end in order to make the size of the struct be a multiple of the register size of the machine. Some platforms have that sort of constraint. Then once we've created this thing, we're going to fill in name is name, and mass is mass. Now, if you're used to Java, you're going to see the syntax here, and instead of using a dot, we're using an arrow. And a dot and arrow serves basically the same purpose here. And actually, if we were to just use a struct directly, then we would be using dots, not arrows. But because the thing that we're using is not a goat, but a goat pointer, we access the fields of our struct with arrows. This is shorthand for, we have GG is a goat pointer. So if we want to get the goat, we have to use a star to dereference it. So then star GG gets us a goat. But then if we said star GG dot, that would be order of operations says that dot is higher priority than star. So we have to put in parens here. And so you could say star GG in parens dot name equals name. that would allow us to access the field, but this is silly enough looking that there's shorthand in the C language of arrow that lets us do field access through a pointer. Alright, so make goat will make a goat and return it. Now, if you remember from last time, one of the rules when we're using the heap, when we're saying malloc, is that every time we call malloc, we're supposed to call free at some point in the program, exactly once, to avoid memory leaks or heap corruption. So if we are calling makeGoat here, and makeGoat calls malloc but doesn't call free, and then returns this pointer, we need to have some way to clean up after ourselves. And a conventional way to deal with that is to have a function freeGoat that sort of releases the goat back into the wild when we're done with it. And it's going to free the goat. But there's a slight complication here. And there's a bug that occurs in both of these. We're going to go ahead and run into that bug, but just keep in mind that there's something slightly wrong here. Now what we're going to do is we're going to write a function that's going to actually operate on goats. And this thing is going to take the fattest goat out of a list of goats. And it's going to say the fattest goat, we're going to start by guessing that it's the 0th goat. We're just going to go ahead and crash if there's not at least one goat in the list. We don't handle the 0 case. Assert is a standard library function that checks a condition and just panics if or aborts if the condition isn't true. Useful for debugging. Then we will return the fattest goat. And then if the fattest goat that we have so far is not as heavy as the goat in the array, then we have a new fattest goat. And we'll go ahead and return the fattest goat when we're done with it. Alright, let's write a test thing for that. So we'll make a goat named Alice, which is 50 kilos. We'll make a goat named Bob, which is 75 kilos. We will make a goat named Carol, 60 kilos. Then we'll make a goat named Dave, which is 55 kilos. We'll say that the fattest goat in the herd is that one. And then we're going to go ahead and make sure that we have freed all of our goats. Let's give this a try and see if we can get the fattest goat. So we need standard IO. we need... Oh, we have a problem. Error unknown type goat. Use struct keyword to return to the type, to refer to the type. So we can't actually talk about a goat pointer. There's no such thing as a goat pointer in this program, because when we say struct goat, this is defining a new type, but the name of the type is struct goat. This is something that you see in a bunch of programming language designs, where when a programming language is adding a novel feature that is sort of scary to some of the people who are approving the language syntax, you end up with a sort of verbose syntax that tries to call out uses of the new feature everywhere it's used so that nobody misses it. Another good example of this is in C++, where every time you try to use generics, you end up having to type class name several times. And then the generic syntax is all trying to call out that you're doing templates all over the place. Luckily for us in C, there's a way to cheat. We have a concept called a typedef, where we can take a type and give it a new name. So when we say struct goat, this is defining a type called struct goat. We can give that type a type alias of goat. And if we do that, then we have a bunch less errors. And so this form here, where you're declaring a struct, declaring it as typedef struct, and then specifying the name twice. The name is exactly the same in both places here, is the convention I recommend for defining structs in C, because then if we have some reason to talk about this as being struct goat, that will work. But in general, we can call the type goat, which is the thing that we want as people who have used sort of more modern programming languages than C. Next thing this is complaining about is that I want standard lib.h. Next thing we have on line 16, so this line right here, we have this warning that our assignment is going to discard the const qualifier from pointer target type. So here we have a const char pointer, but the type here in goat is a char pointer. So we are not properly guaranteeing that we're not going to attempt to change the thing. So of course the thing that we're tempted to do as programmers is just get rid of this const and see if that fixes the problem. But it just moves the... Alright, so we don't actually get the error. That appears to make it go away, but unfortunately it doesn't really make it go away, because the types that we're passing down here are const char pointer types. When you have a literal string, that's a const string. You can't mutate it. It's going to be stored in a region of memory where you can't mutate it. And so this is just taking away some protection that we had that would prevent crashes for certain bugs. So we want to put that const back in. And we want to actually properly handle this. We have a couple different ways of handling it. We can make it so that we aren't allowed to rename a goat. We can put the const here. But maybe we do want to rename a goat. So the solution that I want is we're going to use the stirred-up function, which is going to make a copy of the name. So rather than having a sort of having a reference to this constant name down here, we're going to have the goat actually own a copy of its own name, so we can change the name of the goat afterwards if we want to. And that's going to solve that particular bug. That introduces this other bug here. So the way stirred up works is it's going to malloc enough space to make a copy of the string, and then it copies it. So that means that we have to free that string before we exit the program, or else we're leaking memory. And suddenly we have a reason why we actually have a free goat function rather than just expecting the user to call free directly. So let's give this another try. Next problem is stirred up isn't included. So stirred up is over in string.h. Next problem is that we can't initialize a goat using what? Line 32. So x's is a aha. So this thing is actually a single pointer goat. So we actually want an array of goat pointers here. Fine. We need double pointers to have an array of pointers to goat. I'll get this right eventually. So that compiles. Finally, we find out the fattest goat is Bob. That's consistent with what we're doing. Wonderful. So one thing to ask here is, so when we call makeGoat, that's going to give us back a goat pointer that we later have to call free on. So we call makeGoat 4 times, and then we call freeGoat 4 times. How do we know that we don't need to call freeGoat on GG here? In this particular case, we can tell by looking at the code that the fattest goat function doesn't actually create a new goat object. It's just going to give us a pointer to an existing goat object. And this introduces a concept called ownership. This is sort of important when dealing with manual memory management with, for example, free and malloc. Well, the same thing happens in C++ with new and delete, or Rust with the various mechanics that Rust uses to handle this stuff. But it's probably worthwhile to, every time we return a pointer, we want to say whether or not we're transferring responsibility for freeing that object. So makeGoat returns a pointer that the caller needs to clean up with free goat. So every pointer that we get back from makeGoat, the caller is responsible for calling free goat. And we're going to say that this returns a non-owning pointer, or we could say this returns a reference. And the difference here is that we are being clear in our interface here. This would go in the documentation for this function as well, that you're getting a pointer back, but the fact that you're getting a pointer doesn't mean that you're getting any responsibility to free that pointer. And it's important that every time you call a function and get a pointer back, you ask that question. Are you getting responsibility to free it? In startup, you are getting responsibility to free it, or are you not getting responsibility to free it? And the standard library has functions of both types, so you have to read the man page to figure out what it is. Alright, so that's one version of this goats thing. Let me go ahead and make another. In this one, instead of using a goat pointer, I'm going to go ahead and replace all the goat pointers with goats. So this is actually going to return a goat. So this becomes gg.name, this becomes gg.mass. This is now cleanup goat, and it's no longer going to free the goat itself, because we aren't allocating goats on the stack anymore. Or sorry, we're not allocating goats on the heap anymore, we're going to allocate them on the stack. This is now going to return a goat as well. There's no more pointer here. And then we have to replace all these arrows with dots. This is just going to be an array, not a double array. That's all fine. So this is just going to be a herd of goats. This is just going to be a goat. This is going to be a dot. And so these guys are going to call cleanup goat to free their names. So let's try this. This is, no, this is all correct. So you'll note that in cleanup goat, we're still taking a goat pointer and using an arrow. That's because we're going to pass a pointer to a goat to clean it up, rather than passing the goat object itself. Goats2, goats2.c, goats2. Turns out that Bob is still the fattest goat. Alright, question. If I move this to below the cleanup, is that going to break anything? Think about it for a second, and then I'm going to save this and try it. So now the fattest goat is backtick, bottom accent, capital Y, U. So that did break things. We didn't get a goat name back, we got a sort of messed up goat. And that's sort of weird, because we created these 4 goats. We got a new goat, GG, and then we cleaned up the 4 goats. But none of the 4 goats that we cleaned up was this goat GG. This isn't a goat pointer, it's an entire goat that we have in that variable. But if we clean up the other 4 goats, suddenly we get a corrupted goat name. The problem here, of course, and I can make the problem more obvious if I go ahead and rename Bob before printing. In fact, we will print twice. And then we're going to say herd1.name. 0 is the letter R. So now, before we get to line 52, the fattest goat is Bob. When we rename Bob to Rob, that also changed our goat GG. And the reason for that is that although we have things structured so that logically a goat owns its own name, the goat structure comes with responsibility to, for example, free the name of the goat, our fattest goat function isn't creating a copy of the goat's name, it's just creating a copy of the struct. So we probably want to have a copy goat function which is going to properly copy a goat. So goat gg1 is gg0, gg1.name is stirred up gg0.name. Return gg1. So then here we're going to return a copy of the fattest goat. Then at the bottom we will clean up goat gg. And with that fix, I meant stirred up in copy goat. There we go. Now I run this, and the fattest goat is Bob, because we actually make a copy of the fattest goat in the fattest goat function. A complete copy, not just of the goat structure itself, but of the pointer fields of the goat. Just doing this assignment will copy all the non-pointer fields of the goat. In this case, that's the mass. The mass gets copied here. The mass gets copied by simple assignment, but simple assignment is just going to copy the memory address in the pointer, not the string. So we can fix that. Alright, so that is an introduction to the concept of a struct, the syntax for dealing with it, and some of the complications that we get into with manual memory management and direct access to pointers.